do a better job, and I'll bring in cleanup and so on. So we're going to talk about brick, which again is my history. So my career pretty much has been spent in the brick industry as well as the masonry industry. So there's a lot of things to talk about. I'm going to try to summarize them into some things that you guys can use. And like Amanda said, try to save your questions as we go toward the end. If there's something you really want to address, I'm watching the chat box a little bit as I do the presentation. So we'll see how it goes. All right, so we're here to really, help you deliver better buildings. So not only from the technical side, but also from the installation side, we're here to make sure that all those things sort of come together and make masonry a great tool in your toolbox. Along with Amanda, we do a lot of services for you guys besides education and so on. We do a lot of plan and spec reviews. I do a ton of detail reviews. Feel free to send those over. And be glad to at least give you some comments. You can take them or leave them, however you want and so on. Whatever. Someday we're going to have hands-on. Again, Amanda puts together some great classes and things like that. So at some point in the future, we'll be able to get together again and do some hands-on, which also is a nice learning experience. So again, we think we have the best hands in the business. We certainly train them to be that way, and hopefully that's the way it works out. So today we're going to talk a little bit about the materiality of brick itself, how it's made, and what that manufacturing process does to actually our use of brick. We'll talk about detailing, obviously. We'll talk about how to sort of detail certain wall systems. There are certainly some wall systems that are more durable than others, and so we need to talk about that. And so, sort of that detailing will be throughout. So first of all, I'm going to talk about clay brick. That differentiates itself from concrete brick or other types of brick-shaped materials and so on. I'm going to talk about a fired clay brick, typically made from clay and shale. Clay is weathered rock, and shale is a little bit more of a hardened material that actually has to be crushed. They're one of the most abundant materials on Earth. So, when we talk about sustainability and things like that, certainly the longevity of brick is good, but also the fact that we're actually, drawing natural resources that are, I don't want to say limitless, but certainly are a lot more attainable than some other rare earth minerals and things like that. We're pretty well off. In most cases, they're going to be mined out of the ground, typically surface mines, and then the materials are going to be stored for use later and so on. And I don't know if, again, doing an interactive thing is usually a little bit easier because I can see people raising their hands and so on. But, how many people have been to a brick plant? And again, if you've had a chance to do that. I'm going to turn it down. Yeah, it makes it a lot more interesting and so on.
Got a seminar going on right now.
So some people might want to put their phones on mute. Thank you. All right. So again, you mine the clay out of the ground. You store it. Again, if you're dealing with things like shale and so on, you actually have to crush that material down and screen it to make sure it has the right particle size. When that firing happens, you want to have those particles fused together. And so again, when we talk about the durability of brick, part of that is that you're getting this glassy phase, durability by the bonding of the particles. You're going to form the brick, a couple different ways of doing that, either by extrusion or by molding. You're possibly going to coat the brick. Nowadays, we see a lot more coated brick than were available, 50 to 100 years ago. So sometimes, what's in the body of the brick may be different than what's on the surface. So coating is a big part of that. Then you dry the brick. You try to dry it to near zero moisture content because you're going to put that into a kiln, and that brick is going to be fired to around 2,000 degrees Fahrenheit, and it's going to come out as that durable material, package it, and ship it out to the job site and so on. So, there's really three different processes of making brick, and, which one's more durable than another? Well, they all can be durable. It depends. So the top one is the extrusion method. You can see sort of like a column of clay coming out of that mouth of the extruder. It's going to form two of its dimensions. The third dimension is going to occur when a set of wires comes down and actually cuts it into the individual brick units. You can tell an extruded brick usually because it has core holes. There's actually fingers within that clay column where the clay forms around those fingers. And again, you can have a 10-core brick. It could be a 5-core brick. It could be a 3-core brick. It's up to the manufacturer and what their clays are like. They'll determine, what kind of coring pattern is in there. You can also extrude a solid brick. Again, we'll talk a little bit later about different types of units. but there's no real difference between the durability of a solid unit, 100% solid, and a cord brick. You know, they're both basically going to be the same. We also have molded brick. Two different types there. One is a sandstruck, which I think is the most common. You can also do waterstruck. There's one company in the United States and Massachusetts that makes it by the waterstruck process. But generally, you can tell a molded brick because it has a sandy surface. And really, the sand is really just as a release agent. Now, again, it helps with maybe the aesthetics of the product and so on. But it really is you know, meant to let the clay come out of the molds. And so typically you'll see a molded brick have a little bit more uneven edges. It won't be exactly perfect, you know, and that's the charm of those types of units and so on. The last type, dry press, really, again, is only manufactured by one or two manufacturers in the US. And basically it's sort of like extruding a slug of clay and then pressing it down or repressing it into the desired shape. Now, the manufacturer who does a lot of these dry press brick are actually pavers, not brick for the wall. And again, you know, very specialized. So extruded brick, around 92% of all the brick manufacturers use the extrusion process, and about 7 to 8% use the molding process. So you can see the difference in what's happens there. Now, the one thing is about the different methods is it's going to dictate a lot of things, especially as it relates to appearance. So not only from, you know, a sand coating to non-sand coated brick, but also an extruded brick has a much lower water content than it's made than a molded brick. Extruded brick have water content is around 12 to 15% when they're manufactured. A molded brick are around 30%. So you can see the difference there. So again, when the water goes away, when the brick is fired, you have shrinkage of the clay. So obviously an extruded brick will shrink less than a molded brick during the manufacturing process. And again, so that will relate to you know, the variances in the size. Now, brick is mostly you know, really chosen for color. You know, that's the main reason. Of course, durability is one thing, but again, there's a couple things that need to be taken into consideration. One is grade. We'll talk about that, and the other is type. So, and of course, also the standard that it conforms to. So there's a lot of ASTM standards. Again, as Amanda said, I'm on the ASTM committees and so on. And really, I think that the main one that you really want to focus on here is ASTM C216. You know, it's sort of nice to know that there's other brick standards out there if you need to deal with paving brick or if you're dealing with glazed brick and so on. But C216 is the main one that we normally deal with. Now, also, the physical properties of a facing brick are actually the same as they are with a hollow brick, as they are with a building brick, as they are with a glazed brick. So you're going to see that a lot of the properties go across standards, even though they have their own. So within ASTM C216, again, I'm sure you guys have read that thoroughly. You have if you've been in any kind of problems or had any kind of issues. But in there, there's two things you need to know about. One is grade and the other is type. So grade relates to durability, SW and MW. Now, you know, what that loosely means is severe weather brick and moderate weathering brick. Now, the funny thing is, or interesting thing is, that most manufacturers don't make grade MW unless they make a mistake. They're all manufacturing a grade SW brick because they don't know where their brick's going to be used. And so, you know, they're going to produce it for any particular location. But you still should specify grade SW in your specifications. The other thing is type, FBX, FBS, and FBA. They all have specific meanings. They have specific characteristics. Generally, FBS is sort of the standard, so face brick standard, you could say. FBX is face brick exceptional, one that has maybe tighter dimensional tolerances, the chippage is less, things like that. And then FBA is sort of that molded brick, or even a hand molded brick for that matter. So there, again, you're looking for imperfection to a certain extent, and so FBA doesn't have a lot of requirements that the other ones do. Now, if you don't specify anything and you just say ASTM C216, the defaults are SW and FBS, which is probably going to be perfectly fine for your project, but in some cases, you may need something different. And so that's why it's important to specify those things. Now, again, as you look into the standards, you know, what makes a brick durable? Well, there's three things. It's not just one property. It's actually a combination of a few. One is compressive strength. Another is absorption. And the third thing is called saturation coefficient. So having those three properties together will help you determine whether or not you have a durable brick. So as we see in this chart here, in this table, grade SW brick, the minimum compressive strength on an average of 5 bricks should be at least 3,000 PSI. and each individual brick should be no less than 2,500. All right, that's actually pretty easily made or found. The maximum water absorption, now this is called 5-hour boiling. So there's a couple different ways of, actually 3 different ways of determining absorption. One is 24-hour cold water absorption, and guess what you do for that test? Yep, you stick a brick in water for 24 hours, room temperature water for 24 hours, and see how much water it absorbs. Or you do a brick in a 5-hour boiling water bath, so that you boil a brick for 5 hours. Those are some really exciting tests to watch. So in this case here, the ASTM C216, as well as the other brick standards, they use the 5-hour boiling water absorption as a requirement. And so in this case here, the maximum absorption is 17%. And on each individual brick of that 5 sample, you can go up to 20. The last thing in this table is the maximum saturation coefficient. Sometimes you'll hear that as the CB ratio, because it's basically a ratio of the cold water absorption divided by the boiling water absorption. And there's a maximum amount here. Now, you think about it here. So, okay, so if you put a brick in room temperature water for 24 hours, how much does that absorb? A certain amount. Now, how about if you put it in boiling water for 5 hours? Well, when you boil the brick, you're actually going to force more air out and more water in. So generally, the boiling water absorption is going to be higher than the cold water absorption. So that's why we have this ratio, and this ratio should be really less than 1 in all cases. If you see test results that have a CB ratio or saturation coefficient about 1, there's a problem with the laboratory. So again, what this is saying though is, okay, so 0.78 or 78% of that brick is full of water, meaning that there's about 12% or 22% air potential for, again, we know that when water freezes, it expands. And so we need to have that sort of relief valve within that brick unit for that expanding water to take it into place, into the spaces and so on. So again, if you get up too high to this, now all of a sudden if you get a 0.95 saturation coefficient, you realize, well, there's only like 5% room for that freezing ice to move into and so on. So that's why there's that 0.78 and individual brick of 0.8. Now, just as a comparison, grade MW, has lesser properties. Again, I don't think you're going to be specifying grade MW, especially, if you're doing a lot of work in upstate New York, you may want to have something better than even grade SW. Now, the one thing about brick, again, they're made in many different ways. They're made with many different clays. And so, some of the rules don't always apply. And one of those things is if your saturation coefficient, that can be waived if your cold water absorption, not boiling, but cold water absorption is less than 8%. So they've determined this by testing and research over the decades and so on. And they find that really if your brick doesn't absorb water, you think like a piece of glass block, the water can't freeze into ice because there's not enough water in there to actually have that occur. So in some cases, you can have a very hard, dense brick that doesn't have to meet this saturation coefficient because it's going to have an absorption around 4 or 5%. So again, there's a lot of very hard burn brick out there that have a cold water absorption 3 to 4%. Again, they're not going to meet that saturation coefficient because again, in some cases you really can't determine that very easily. So that's one way. Now, another way that's again not done very frequently, but is an alternate, is the 50-cycle freeze-thaw test. And what they have here is they actually put the brick and saturate it in room temperature water, and then they take it out of the bath and then they freeze it for 24 hours. And then they thaw it for 4 hours. And then they, again, saturate again and freeze it for 24 hours. And then thaw it. And they do this for 50 cycles. And this is sort of to show, what would happen out in the real world. Now, again, the interesting thing about the 50-cycle freeze-thaw test is, the freezing is coming from all directions. In a wall, you're going to have freezing occurring from one direction, and certainly saturation generally from one direction. So this is a pretty severe test. So it's like 50 cycles. You can go through 50 cycles in one winter, and so on. Well, that may be true, and so on. But again, it's the idea that this is during a saturated condition, which isn't very often, and so this will simulate that. So some people say, well, why don't you do 100 cycles or 300 cycles? And again, you could, but you're going to find out that after 50 cycles, you're going to know one way or the other. So again, so that's the durability of brick. So again, now in the old days, a couple hundred years ago and so on, they were able to tell the brick by smacking them together. And if you heard a ring, then you know that you had a good hard-fired brick. If you smacked two brick together and they thudded, well, then, that's a clunker, and so they may not be quite as durable. Now, you can't do that as much today just because of, the way the brick are made and so on. But certainly that would be a way to determine things as well. So we have more sophisticated ways in using different properties. Now, here's a chart that, again, sort of goes beyond what ASTM says. So here's the ASTM requirements here on the right-hand side. So 3,000 PSI, again, there's no limit on cold water absorption. The boiling water is limited. The saturation coefficient, and something called the IRA, or initial rate of absorption. That's a third way of measuring absorption. This matters when you're trying to lay brick with mortar. And we'll talk about that a little bit later, too. Now, most of the extruded brick that are manufactured today, and again, this was done a few years ago, but again, would still hold true today. But the average of extruded brick that are made in the United States are around 11,000 PSI, much, much higher than ASTM. So again, that's a number that is not a big deal. Now, when you look at molded brick, again, you think about how they're made. They're made with more moisture into these mold boxes. Again, we have a lower strength, which doesn't necessarily mean that they're worse. It just means that that's what they have. Now, the other thing to notice here too, then, with molded brick is the saturation coefficient is always around 0.6. So again, remember we said that we want to have enough space left over in those pores for that ice to form into and so on. So with a molded brick, even though it has a lower strength, the pore space is distributed very well. So that's why you can have a brick from Colonial Williamsburg still performing today as compared to one that may not. Now also look at the extruded brick. Again, the saturation coefficient around 0.6 on average. Again, the limit's 0.78. So in many cases, we're going to see that the saturation coefficient is waived on a lot of brick, because in most cases, again, that those extruded brick have cold water absorptions that are less than 8%. In this case, the average is 5.4 in the United States. All right. Just a couple, things as I'm continuing past here. Also look at IRA. So again, how much water does a brick suck up, when it's laid in a fresh bed of mortar? And so in this case, the IRA, which is measured in grams per minute, again, 16 versus molded, which is around 36 on average. Now, again, if you have seen your brick specifications or know anything about IRA generally, you have to limit the IRA to about 30, and anything above that, you should wet the brick before they're laid. Again, you can also see, how many times that occurs. So you can see, again, a molded brick generally will often have that IRA above 30, whereas an extruded brick will not. So that's a different situation, but I wanted to at least let you guys know, where these things fall when you talk about the different manufacturing methods. So, on the left-hand side, we have these examples of brick that have lasted for hundreds of years, I guess 1,000 years, I guess you could say, thousands of years. On the bottom left-hand side is a building, Adam Thorogood House in Virginia, that's lasted for at least 300 or 400 years. So we have these examples of brick lasting for a very long time, but then we go out to a project and we see these brick that are spalling. Spalling is the technical term for deterioration of brick. And it's like, well, why is that brick spalling? Again, well, it must be a bad brick. Maybe the fire didn't get all the way through the brick and things like that. That could be the case. But again, we have the ASTM standards to at least help us, alert us like, hey, we're looking at some potential good or bad brick here. But maybe it's not just the brick. Maybe it's the environment that it's in. And so again, how much saturation the brick sees, that's another big determination of durability. So again, the durability is not only affected by the saturation, again, not the absorption necessarily. What we care about is how much that, brick is saturated and how long it stays saturated, especially during freezing temperatures, but also the trapping of moisture. Again, many of you have heard that, BIA and other groups don't recommend clear water repellent coatings on brick, or sealers, because they can trap moisture in there. And that's exactly right. I mean, we want these walls to breathe to a certain extent. We don't want them to leak, but we also, if water does get in, we want it to breathe. Now, again, we're looking at all these very tight buildings, and, we're having issues with mold and, of course, indoor air pollutants and things like that. And in the past, our walls were relatively leaky. And so, again, if there was some moisture that, rain or whatever got into the wall, those walls could much easier evaporate the water out. Now that's only, in many cases, just going in one direction, back to the exterior. in the past with these, multi-wife brick walls, these mass walls. Again, we had evaporation occurring in both directions, inside and outside. And now it's really just relegated to the outside. So we have to be a little bit careful about that. But again, saturation and the trapping of moisture are things that also affect the durability. Where do these moisture sources come from? All over the place. From rain, from condensation, from rising damp. Don't see that too much anymore, and so on. But again, so water's coming in from a lot of different directions, and we need to deal with that. Now, again, in the past, we had mass walls, which worked perfectly fine when they were very thick. But as the walls got thinner and thinner, all of a sudden our reservoir got smaller and smaller, and so instead of it staying within the wall, it started to leak to the interior. And as that happened, then we start developing cavity walls. So again, the cavity wall is a drainage wall system now that if water does leak in through the outer face, we have a cavity or airspace to help drain the water back down and back out again. And again, we also have air barriers in our wall system. In some cases, we have vapor barriers within our wall system. All those things help us to mitigate the problems with moisture. Now here's a thing that I've been told from other groups and so on is the 4 Ds: deflection, drainage, drying, and durable materials. So these are the sources to reduce water penetration. So first of all, keep the water off the wall in the first place. And we'll talk about that. How do we do that? Drainage. Again, we've now implemented drainage wall systems into our walls, into our designs, and I think that works out well. Drying. This is one thing that I think we're starting to, sort of learn a little bit more about, but actually have a vented cavity wall or a rain screen. So again, why do we keep hearing this word rain screen all the time? Again, masonry had been a rain screen of some type for decades and so on. And so now, maybe we need to look at that. And of course, durable materials is one of the things we're talking about here. So how do we deflect? How do we keep water off our walls? Well, part of this goes to architectural design. And so this is part of our problem. So we don't design our buildings like we used to that had large overhangs on our buildings, and that helped deflect the water away. Our buildings are very sleek, they're very modern, and so there's not a lot of these overhangs to help us out. So again, having something at the cornice that would help redirect water, something at the window head that would redirect water, something at the window sill that redirects water, and at the base of the wall having some type of water table. Again, some of these things aren't within our current architecture, but they all are very important. So again, we look at some of these older buildings. The one on the right-hand side, again, has some protection. Now, it's not going to protect this building totally from rain, but again, it's certainly at the top of the wall where things are most vulnerable from wind-driven rain. That's where the cornice does do its job. On the left-hand side, you see a building that it's sleek. So all the water that comes onto that facade is going to be absorbing into it. So again, so now the materials are being asked to do a little bit more than they were in the past. The window head, again, we had pediments and other types of architraves that are on top of these openings that, again, help redirect the water out. Now, this is the National Building Museum down in Washington, D.C., and you can see, I'm not sure that this flashing was there originally, but again, over time, they realized that, hey, maybe we need something a little bit more sufficient to help, get the water off the top of that. But then again, this also helps, deal with water getting into these window head areas. Windowsill, here's a picture from Chicago, again, some 1800s, maybe 1900s building, again, where they have different belt courses and at windowsills to help redirect the water out. So now, instead of the water sheeting down the entire facade, now we're stopping that water as we go down. And then water tables. So again, most cases, water tables are really just a change from one thickness of a wall to another as you go up the wall. But again, it also helps, deflect water in many cases. So here's some contemporary examples. So you say, well, we don't do that kind of detailing or design anymore. You can, again, so here's something at the University of Pennsylvania where they've actually used a different material to use as possibly a sunshade, but also as a certain amount of overhang. Again, same kind of condition here where we're using different materials to help redirect the water out of these off of these walls. And it goes back to have we learned anything? The wasn't it Vitruvius who, didn't he have some books on architecture or something like that? Have we been paying attention to some of that or not? I don't know. Maybe we have, maybe we haven't. So here's some typical facades in Rome. And they had different band courses. They had different window hoods and sills and things like that. And again, those buildings are still around because, again, they managed water maybe a little bit better than others. So on the left-hand side, we can see where, again, water would be deflected at each floor level, whereas on the right-hand side, now we have these planar facades, which, again, the water is sheeting down those areas. And again, our materials, masonry materials, are certainly pretty decent, but again, they're being asked to do a lot more. So, and this is, again, as you saw on the previous slide there, Matthew Bronski from Simpson, Gumperson, Heger gave me these sets of slides. He gave a presentation one time, and I thought, oh, this really makes sense. So you can see on the left-hand side, again, how the water absorbs into the wall system, again, but is redirected at the floor levels compared to some of the walls we have today, which, again, absorption is occurring all the way down the facade. So, again, just something to consider. Again, it may not fit within your architectural style, but something that can certainly help. Now, I like to base a lot of my recommendations off research and so on. So here's the Canadian Housing and Mortgage Council did some studies back in the 90s, and they looked at different overhangs on walls. So in this case, this is millimeters and so on. So, but you can see that problems occurred when there was minimal or no overhang. When you had overhangs, decent sized overhangs, again, the water problems were lessened. So again, certainly in coastal climates or areas where you see a lot of moisture, these are things that can work to your favor. So let's design for that if we can. All right, so that was deflection. Again, challenging to do that to a certain extent. The other one's drainage. And I think this is a lot easier. We've been dealing with drainage walls and cavity walls for a long time now. Again, we want to, if water does get through that outer brick white, it gets down to flashing and out through weep holes. Now, there is a famous consulting engineer who said, no 4-inch width of brick masonry, no matter how built, by whom, or of what, ever stopped a wind-driven rain. And you know what? He's right. I mean, in most cases, a brick veneer won't stop totally wind-driven rain. And so, we need to have some mechanism to take care of that. And we have. We've designed these walls, to work out pretty well. So that airspace, is not only in there for drainage, but also remember, it also could be in there for drying too. So we have air in, just due to, natural buoyancy of warm air, it's going to rise a little bit and potentially go out. If we have vents at the top of the wall, not all walls have vents at the top, but if they do, now we can let air out. And of course, we're also trying to get the water out just due to drainage. So we can actually make these wall systems more like a rain screen. Just a couple little details here. Cavity versus airspace. This comes into play when we talk about wall ties and how far they can span. So the cavity is the distance from the back of the brick to the exterior side of the backing. All right, so that's the cavity. And then the airspace is left over after you put insulation in the cavity. And again, 20 years ago, we weren't putting insulation in the cavity, but now we're doing it pretty much every single time. So that's the difference between a cavity and airspace. And that's more of a technical issue, but something you probably should follow. Now, the code says that cavity or airspace has to be at least 1 inch. The TMS 402 or ACI 530 code, that pretty much mandates that requirement. That code is referenced by the IBC, which, basically becomes law. Now, a lot of the industry associations, like I said, I used to work for the BIA, and, our recommendation was always a 2-inch airspace. And really that, it just helps keep the cavity clear. And if there is any kind of mortar bridging, it's kept to a minimum and so on. But, nowadays, I'm not as concerned about the 2-inch requirement because we have air barriers. We have weather-resistant barriers in our wall systems. We have insulation in there. The insulation may be taped. There's a lot of different ways now to resist moisture going all the way through the wall. So, while I definitely agree with the 1-inch minimum, certainly, more would be better. But again, because of our insulation thicknesses, our cavities are starting to get pretty large. I'll talk about in a second here about maximum cavity size, which is 4.5 inches. So we're starting to get to there in some situations. And, I guess I talked about this already. I mean, again, don't forget about things like recessed courses. So if you have a recessed course and pushing that in an inch and you only have an inch airspace, you've just closed your cavity off. You closed your airspace off. So again, having a little bit larger airspace will allow those kind of details to occur. And maybe, we often see things like efflorescence on masonry walls. Hopefully not, but sometimes that occurs. And maybe if our walls are drying out more quickly, the chances for efflorescence to occur will be lessened. And so a vented cavity wall is not a bad idea. As I mentioned before, the minimum size is an inch. The maximum size is 4.5 inches. Now, as we continue to move on, the 2018 IBC will reference the TMS 402, which is the masonry code, the 2016 version of that. And in that, they actually increase the airspace to 6 5/8. Now, there are a couple little particulars you have to follow with that and so on. But again, because of the insulation, again, in upstate New York, we're putting 3 inches and 4 inches of insulation in our airspaces. And so, having enough space for that, as well as the airspace, insulation and airspace, again, will kick us out to some of those larger distances. Now, remember, though, I mean, you can design a wall tie to do anything. If you actually start analyzing some of the wall ties and typical wind loads, you can find that you can go to 6 or 7 inches without a problem. Now, on the right-hand side, we have a picture of, it looks like a corner element and so on, and that cavity is a little bit large. So, maybe that should have had some infill or something like that. That's probably a little bit too far for a wall tie to extend. I mean, but again, if you did some testing, you could find out, whether that would be appropriate, especially for this small element. Now, on the left-hand part of that picture, though, you see the airspace. That's pretty thin. Now, again, they are using some type of a drainage mesh as they go up the wall. Again, that's not a total relaxation of some of the requirements. We would still like to see the 1 inch airspace. So that may help a little bit, but again, so that cavity is a little bit smaller than I would like. So along with drainage, again, we have our airspace. Now we also have flashing. Flashing is going to be at the base of the wall, under window sills, at window heads, if you have shelf angles in the wall, and at the top of the wall under copings and so on. So again, anywhere there's discontinuity in the cavity is where you would put flashing. And again, I'm going to sort of breeze through this part because, again, I assume you guys have heard this before and so on. But again, we want to put flashing at the base of the wall. We want to put flashing under windowsills. We want to put it at under copings. We want to put it at shelf angles. Don't forget, though, about things like this. So we have this higher wall and lower roof condition. It's like, oh, well, I have a roof flashing there. Where the roof flashing is only occurring on the outside face of that brickwork. Now, remember, we said earlier that we sort of assume that water gets through 4 inches of brick weight. So if water's running down the backside of this brick in this kind of condition, where's the water go? Well, you really need to have through-wall flashing at this location for that to work. And I'll show a detail of that as we go through. But those are all good locations for putting in flashing. So again, you guys have heard it before. You want to have the flashing at least come out to the face of the wall, if not form a drip edge. So on the left-hand side, that's bad because the flashing is held back from the face. And so again, you can see what's going to happen here. Water's going to come down this flashing. It's going to go right into the core hole of the brick, or it's going to sit on the steel and cause corrosion. So again, if you're a firm that works in forensic engineering and does a lot of restoration, go ahead and let that happen because you'll have future work for sure. What we want to see is the flashing at least come out flush with the face of the wall. And then again, forming a drip edge would be a bonus. So, good, better, best, as we go through here. Flash materials, again, I assume you guys have had lectures on seminars on this. Anything that's more durable would be better. So again, stainless steel is great. Of course, that's hard to work with. So a lot of manufacturers now have stainless steel composites where they have thin sheet of stainless steel along with polyethylene on it. And that works out pretty well because it can be bent in the field a lot easier. Again, we have end dams and other types of things to make corners. So whatever it is to make it easier on the mason to install that, the better. EPDM, we see some of that. Again, that's more of a roofing membrane than a flashing, but that certainly can be used. We see a lot of the self-adhered rubberized flashing. That's very ubiquitous around the country and so on. So that provides some durability, but also provides some adhesion. So it maybe helps keep wind-driven rain from blowing up underneath. On the right-hand side, I show a picture of copper composites. I just don't see that too much anymore. Again, copper is expensive and so on. I had, back in the 80s, I saw a lot of asphalt-coated copper. And it's like, what are we using these for? Again, the asphalt's in some cases stained and things like that. This is a craft paper coated copper, but again, I think I see more of the rubberized asphalt and the stainless steel composites in most cases. So remember, the flashing is a system, though. It's not just a flashing. So again, we have not only our flash material here, but we have a drip edge. We also have the corners all sealed properly with appropriate mastic that's being used. We also have a term bar at the top here. So termination bar, again, we didn't see that too much in the past, but we're seeing that a lot more because, again, you don't tuck the block or you don't tuck the flashing into the block course anymore because the walls go up separately. In the old days when brick and block went up together, that probably 1950s, you could do that kind of designer detail. But nowadays, the block's already up, the brick comes in later, so a termination bar is important, again, filling all the holes and then sealing along the top edge. Because again, if water does get across this cavity, we have to be wary of that. Now, again, in most cases, with now, air barriers nowadays, you're going to see some type of an air barrier coating. So that air barrier has to be used in combination with the flashing to work as a true system. Now, the other thing I want to mention is, there are some materials that just aren't meant to be flashing materials. So aluminum corrodes in fresh mortar or fresh concrete. So you don't want to use aluminum as flashing. Polyethylene sheeting, building felt, that's crap. That should not be used as a flashing. Thin PVC, the Novastraw, you've heard that term before. Those are just very thin materials, and that's part of the problem. So again, they should never be used. We also have people, talk about concrete being, especially at the base of walls, like, well, I have a concrete foundation here. Water's not going to get through that. Well, there's always been some truths that have been told to me. One is that all windows leak and all concrete cracks. And so if you're, using untreated concrete as a flashing, that's questionable. Now, some people say, well, I'm going to put a waterproof membrane and that could act as my flashing. Well, maybe. Again, if you're sure that the crack is not going to occur within that element that would allow water to get into the cracks, then you're okay. But so yeah, there might be better ways of doing things. Again, good, better, best is something we like to promote here at IMI. Again, end dams, on flashing materials, we want to get the water out of the wall as quick as we can. We don't want to let it go back down into the wall system. So again, things like that, just an inch or so, just to help redirect the water out. And, we get a lot of flack from talking about drip edges. Again, it's like, oh, well, this affects the performance of our wall and aesthetics and things like that. Well, again, I like to point out, pictures like this where, again, there's no drip edge at all. Now, again, this is I guess a window sill condition, and the water is just sheeting down the window, of course, not absorbing into the window at all. And now it's taking any kind of pollutants and washing them down into the brickwork. Now, think if we had a drip edge there that helps force the water away from the wall. What kind of, situation would we have then? So again, even though, again, these thin metal strips, may be exposed, again, you're telling other architects like, hey, I pay attention to the Masonry Institute and we do things the right way. Whatever. So again, drip edges, definitely help the situation out. So, this is what we see a lot of is rubberized flashing with the stainless steel drip edge. Again, whatever material you're familiar with and so on, whatever works for you is fine. But generally, we have a stainless steel drip edge. Sometimes it goes, a couple inches into the brickwork. Sometimes I've seen that goes all the way through and then gets turned up. I think maybe that's a little bit overkill. But again, depending on, the requirements of your project, you may determine that that's critical to your facility and so on. Sealing this down, in some cases, actually putting a sealant beneath here as they lay this stainless steel drip strip. Again, all those things help reduce the amount of potential wind-driven rain from getting into the building and causing problems. So again, deflect, drain, dry, whatever we can do to keep the water out is what we want to use. So here is an example. They put down a single bead of caulking here, sealant, and they're embedding their stainless steel drip edge in there again. So wind-driven rain, really will not be an issue. And then they're going to bring the rubberized asphalt on top of that. That then adheres down to the stainless steel drip strip and works. And butt joints. Again, this is another thing that depending on how annual you are with detailing and things like that. If you have a butt joint, how do you seal that properly? A lot of times you want to overlap it. If you overlap it, then you see a little bit of an increased size and thickness. So there are right ways of doing that and the wrong way. And again, we train our craft workers to do it the right way. Mortar collection devices, you know, again, we don't recommend proprietary materials, but things like mortar net and products like that are probably a good idea. You know, again, they keep the weep holes open. We want to want to let the wall dry, and so that's one way of doing it. We also want to consider, again, venting the airspace. So not only do we put the vents at the you know, weeps and vents at the bottom of the wall at the flashing location, we also put at the top of the wall. So again, you can see here we have a weep hole, or in this case, this is actually a vent at a shelf angle location. So this is the shelf angle. They have flashing, they have weep holes above, and then we also have weep holes below. In this case, it's more of a vent. On the right-hand side, this is actually Cornell University. Those of you have been up there, the Alice Cookhouse. These are actually vents to the airspace. Again, they're using this more as a pressure equalized rain screen wall or pressure moderated rain screen wall. And so not only do they have vents and weeps at the base of where the flashing is, they also have vents here. And again, these also act as vents. So that, again, is allowing our wall to dry. And again, another example of that situation. Remember, you know, put the weeps or vents below the coping so that they're actually exposed. And again, I'm not, you know, I don't care a whole lot on what you use as a weep. Again, I would say stay away from plastic tube and rope wicks. I mean, that's old style stuff. Again, those don't drain very well. And again, if we're trying to vent the wall, trying to make it more into a rain screen wall, then certainly those don't work at all. But the other ones certainly do. I've also seen some people using weeps as in a horizontal fashion. Again, if you have a one-piece sill, you know, how do you have a weep? Now, in most cases with a one-piece sill, you really don't need a weep. Again, where's the water coming from that you're trying to direct the water out? But in some cases, if you want to do that, you know, here's an example of that underneath a stone sill, or in the bottom left-hand corner is in a rubble stone wall. Now, you know, we talk about drying and so on, and we get moving into these, you know, ideas of rain screen. In this case, this is an open rain screen wall. So now we don't have joints. We allow the water and air in, but we're also trying to equalize pressures across that. So we have an air barrier in that whole wall system that helps allow this whole thing to drain. So again, brick have been rain screens for a long time, but now we're even more sophisticated. We're putting more venting in there for that to occur. The last thing I wanted to go through is just talk about some special conditions, below grade masonry, window sills, and copings, where again we see moisture issues degrading the brickwork. So, you know, below grade masonry is don't put brick below grade. So, you know, that's a recommendation. Now, again, we see a lot of cases where it's like, no, I'm not going to have an exposed concrete foundation. I want to take the brick below grade. So if you do that, then again, make sure that the brick units are durable. You know, maybe make sure that they're having some properties like a paving brick. You know, put in a mowing strip, you know, some gravel along the base of the building that allows any water to, you know, stay away from the brickwork itself. Definitely grout solid behind there. That's always a recommendation. That last course of flashing. Anything below that should be filled solid. Again, we usually put insulation in there nowadays, but you know, that's you know, helps keep the water out. And again, make sure that those you know, flashing and weeps are above grade, because once we get below grade, even though you think it might have some sort of French drain kind of system, that French drain usually gets clogged up. So yeah, so again, you know, this is more of a retaining wall to a certain extent, but again, we can see that there's a lot of moisture here, not only, you know, running down off of the concrete onto the brick, but again, you know, soil conditions behind there. Now again, this efflorescence is most likely due to all this runoff. But we also have situations here where, again, we have brick going below grade, and that's causing a certain amount of rising damp, which can lead to staining, if not durability issues. In many cases, you know, like we did in the old days, where we actually put granite at the base of buildings. You know, what happened to that? So again, this looks more of like a residential project, but again, now they're paying attention to that. It's like, okay, let's make something more durable than you know, some of the material that might be below grade. We talk about high performance wall systems. Again, we have these kind of situations. We want to minimize thermal bridging. So again, we're seeing this overlapping of insulation. I've seen some insulation go all the way down where they have two split walls of block. You know, that sort of is duplicative to a certain extent. So I see this working. So again, any kind of thermal bridging would have to work its way all the way around for this to really be a problem. And again, there's all sorts of thermal bridging guides that explain some of that, but that's one way of dealing with the basement wall kind of condition. Windowsills, again, if you don't put flashing underneath the windowsill, you'll have conditions like this. Whatever. Again, I think that this is an exposed area that we just really need to address. And again, so sloping is probably one of the best things we can do. Slope it away from the window, and that'll do more than anything else. We can also, look at our different materials. Again, anything that's more durable, stone, metal, those things are good. And really, the fewer joints, the better. Now, I love brick, but I'm not a big fan of a brick roll-up course because, again, I think they're more prone to problems. So again, here's a situation on the left-hand side where this is I'm not sure if that's 15-degree slope, but that's getting close to it. On the right-hand side, it's flat. And well, in some cases, it's a little slope just because the workmanship's not great. But again, this building's probably over 100 years old. We also like to see an overhang. So again, water is going to run down the window. It's going to saturate the sill, and it's going to run down the rest of the building. And so in this case, on the left-hand side, it's a coping. But again, the same kind of situation would be best if we can actually, allow some type of an overhang. The joint should be as narrow as possible. Again, I think this building probably has had some repointing work over the years and so on. Of course, it looks like they have some structural issues there too. But again, we want to try to keep those joints as tight as possible because, again, brick is durable, but the mortar's not, at least not for the long term. So we need to do that. And the sills need to be maintained. That's the other thing that we need to convince owners that we need to look at these types of things. Again, having end dams on flashing, that works out pretty well. Again, we're going to put that brick roll-up course or whatever sill right on top of that, and that looks like a pretty decent way of keeping water out. So we also get into these kind of situations where it's like, oh, you know what, I'm gonna put the flashing down another course, and that way I'm gonna give my this whole element and maybe a little more heft, a little more beef to it, so that it can stay on the wall. Well. Again, what that does is that now exposes another course to water penetration and saturation. So really, we want to have the flashing directly beneath the sill. And again, we're going to have to attach it back. It doesn't matter whether it's one brick or two brick. So having some type of wall tie or whatever holding it to the backing is going to be necessary. And you're going to puncture your flashing. So again, that's why I like having more of a one-piece sill than having a brick roll-up course, which is going to have to require wall ties periodically along its length. By the way, at our website, imyweb.org, we have a lot of details. This comes from our masonry detailing series. Again, how does this all get put together? So this is sort of a good little training exercise for some of that. The other thing we also see some water penetration issues is recesses and projections. And, again, maybe they're not very large. So maybe, this is a pretty minor type of recess. So maybe that's not a big deal. But as you get further and further, you start to run into some problems. Now, again, in many cases, if you say, well, I don't want to have just a half-inch reveal. I want to have something like an inch or an inch and a half. Well, that's pretty large. And so maybe you can use different color brick units to accentuate what's happening there. On the left-hand side, that's San Francisco Museum of Modern Art. That's actually as a brick face precast panel that's actually been used with more of a full depth brick to make that occur. So what we generally say is, really you want to try to keep that recess to about 1/2 an inch to 3/4 of an inch, especially in severe weather climates. Now, again, remember from just a stability standpoint, you don't want to go too deep because now all of a sudden the brick doesn't have proper support. That's usually about 1/3 the bed depth, which is about 1.2 inches. But also remember that the brick manufacturers are allowed to have core holes as close as 3/4 of an inch to the face. So unless you specify a 100% solid brick, again, that could open up the core holes to water infiltration. And that's not a great situation. We also like to see some type of mortar wash on there. That mortar wash may not last forever, but again, it'll do a pretty good job of helping redirect some of the moisture. And in some cases, especially if it closes off the cavity, maybe having flashing at that location might not be a bad idea. Copings, tops of walls, again, this, same kind of situation when we talk about sills. You can have different types of materials. Overhangs are important, flashing and anchorage. Again, anything that has less joints is what I'd recommend for a coping. I'm not a big fan of a brick coping especially, brick sills I'm not a big fan of, coping them even less. So again, terracotta certainly has been used in the past, and that can work. Again, whatever it is, we want to have, a couple different layers here. We want to have the coping itself, which is sloped mostly to the inside surface and so on, interior of the roof. And then you want to have some type of flashing underneath that. Now, again, it's like, well, I've just broken bond. It's like, yeah, you have. But again, we're trying to protect moisture from in here. So yeah, you need to put the flashing in, through wall flashing, and then anchor the coping down. And here's a couple different ways of doing that. Again, our masonry detailing series shows this. Stainless steel. Here's rubberized asphalt on the right-hand side. They all seem to work. Again, the only thing I worry about here a little bit is the flashing sag. So maybe a metal coping or metal flashing would have been better here. No flashing and efflorescence. So again, we're having some type of moisture issue here. Maybe it's through the joints, maybe it's through the water runoff with a little minimal overhang. But again, flashing underneath there would have helped the situation out tremendously. Don't really get into wall ties a little bit, just to say that, from a durability standpoint, again, we've been using hot dip galvanized wall ties for decades now. Maybe it's time to move to stainless steel. That definitely is a higher durability, and in some cases, it's a lower thermal conductivity. People have been talking about thermal bridging and so on. Now, wall ties are really a very, very minor thermal bridge. But again, if you're concerned about that, stainless steel can help you out. We also want to have some type of cover on top of that wall tie. 5/8 of an inch is what we like to see, and then a certain amount of embedment. Otherwise, you're going to have the situation shown on the left-hand side where the wire's corroding, and it's actually causing the mortar to pop out of the joint. So again, we need to have some type of coverage there. And then things like corrugated wall ties, just don't do it. They're very thin, and the corrosion protection is very minimal in there and that kind of stuff. So when we talk about durability, this is the least durable of all wall ties. Again, mortar joints, same thing. We want to promote durability here. And so again, tooling the mortar joint does a lot to protect the wall. So by compressing the face of the mortar as that wall is being laid, it's going to do a really good job. The other thing to know is that really the number one thing to reduce water penetration into walls is to fill the head joints. So again, here's pictures here where, again, this is not good. This is not good. This is not good. We want to have as full of a mortar joint as we can. And that really is one of the big things to keep water out of our walls. So some of the tools that you guys have for quality installation, developing those adequate details and specs, pre-installation meeting. We're free to help you guys do that with our mason contractors. Do mock-up panels, especially when you have very complicated air barrier transitions and things like that, and flashing transitions. A mock-up just does a great job of helping us understand all that. Again, know who to call for support, and again, helping, require trained craft workers would be good. So, specifying durable materials in the first place, keeping the walls dry, designing detailing for water penetration. Again, we do that a lot with our drainage wall systems. Overhangs are our friends. Follow industry recommendations where you can, and use trained craft workers to accomplish your designs. So I just want to finish up here, and you guys can start putting into the chat box any questions you guys have and so on. But I thought I'd run through here and just show you some pretty unique examples of different types of brick structures that, hopefully will be durable. Here's a net zero energy building. Masonry can be used in all sorts of different types of projects. Here's a project in London with a perforated screen wall. I've just given a couple presentations along these lines about how to do this properly and so on. There's not a lot of guidance out there, but that's pretty cool. Again, using very rudimentary products and so on. Here's a project in Thailand, very thin mortar joints and so on. But again, they've created this really interesting articulated facade, which is, I don't know, it just interested me a lot. More perforated walls on different sides. This is a project at Yale University. Again, they've used a brick shape at every other course. Again, some clients have more money than others and so on. But that's pretty cool. Now look what they did though. They thought about, what happens with the water that sits on, these brick units. So they've actually left this joint void so the water can drain down more easily. And then they've tooled the mortar joint back against the wall. So again, they've given some thought to that as well. And sometimes, again, just how you design walls. It's really working with the craft worker to make this all work. Again, this is a solar screen outside of project in India and so on. That makes a lot of sense. One in Switzerland, and here's one in China. So again, brick can be used in very, very many different ways. I mean, even Frank Gehry uses brick. So, if he's using brick, now again, it has to be something very interesting and so on, very curved facade. I think they call this the crumpled brown bag, I think is the moniker they've used for this project and so on. But it is pretty cool. And, so here's a glass brick project. This is in Amsterdam, clay brick above, and then it sort of filters down into a glass brick facade. So, is this the future of masonry? We'll have to wait and see. So. All right, so we're getting some questions. Will you be willing to share your presentation? Yeah, so I'll work with Amanda to help have that available and so on. So we'll figure that. How big of an area is enough to be representative of type of brick for a mock-up? Yeah, so somebody actually answered that. 4 square feet is usually a good element. So if you're doing more of a sample panel where you're trying to look at color and things like that, 3 foot, 4 foot is about the minimum size. For a mock-up, actually, I mean, I might even consider something even larger than that. I mean, I've seen where they're at least 15, 20 foot wide, well, maybe not quite that large, but 10 foot wide, and then a whole story height up. Because again, you're trying to incorporate the window head, the window sill. You want to see what the transitions are and things like that. So from a mock-up standpoint, again, I think the bigger the better. If it's just really for color and things like that, that's where the 3 or 4 foot comes into play. Other questions? Again, some of this is rudimentary and so on, but again, I like to remind people of why we're designing certain things the way we do. And I think, again, if we stick to the recommendations, I think we'll have a fine form building, and you can finish your work for the holiday and be happy that your buildings are going to last forever. So seeing no other questions and so on, Amanda, I'll turn it back over to you if you have any parting words of wisdom.
Well, no, thank you so much, Brian, and thank you guys for attending. Like I said before, if you're looking for a credit, shoot me over your AIA number, and I hope everyone enjoys the rest of the week.
All right, guys, have a great day.
Thank you. Bye.
Thanks.